Hello everyone, my name is Ahmed Manzoor and I will be your adjunct professor for general chemistry this fall 2025 semester. I'm excited to join you in this journey through the fascinating world of chemistry, where we will explore everything from atomic theory to chemical reactions and the principles that govern matter at the molecular level. My goal as your instructor is not only to help you understand the core concepts of general chemistry, but also to help you build the problem solving and critical thinking skills that are valuable in any scientific or health related field. I encourage active participation, curiosity, and a growth mindset throughout the course. Please feel free to reach out if you have any questions or need support during the semester. My job is to support your learning and success. So, throughout the semester, we will be using the 7th edition of Introductory Chemistry by Nivaldo as our primary textbook. This book offers clear explanations, real world examples, and helpful practice problems to support your learning journey. Let's begin with chapter 1, where we will explore how chemistry is part of everything around us, even something as simple as sand and water. You will learn that ordinary things are made of chemicals, and chemistry helps us understand their properties and behavior. We will also introduce the scientific method, the way chemists think and solve problems through observation, experimentation, and reasoning. Next, we will practice analyzing data and drawing conclusions, a skill you will use throughout this course and in real scientific work. Finally, we will talk about how to succeed in chemistry with the right mindset, study habits, and curiosity. You are more than capable of mastering this subject. So, what is chemistry and why it matters? As we all know, chemistry is a study of matter, its composition, properties, and how it changes. Everything you see, touch, breathe, and consume involves chemistry. From developing medicines and renewable energy to cleaning water and cooking food, chemistry is a central science that affects every aspect of our lives. Learning chemistry helps you think critically and solve complex problems, understand everyday phenomena scientifically, and also build a foundation for careers in health, science, and engineering. So now that we understand what chemistry is and why it matters, let's take a closer look at what everything is actually made of. At the heart of chemistry is a simple but powerful idea. All matter, everything around us, is made of atoms. So next we will explore these atoms, the tiny building blocks that make up all substances, and see how their structure determines the properties of everything from air to metal to living cells. The most important idea in all scientific knowledge is that all things are made of atoms. Why is this idea so important? Because it establishes how we should go about understanding the properties of the things around us. If we want to understand how these matter behaves, we first understand how these particles that compose that matter behave. For example, sand, like all other kinds of ordinary matter, is composed of atoms. Atoms are unimaginably small in size. Even a single sand grain contains more atoms than there are sand grains on the largest of beaches. Atoms and the molecules they compose determine how matter behaves. If they were different, matter would be different. The nature of water molecules, for example, determines how water behaves. If water molecules were different, even in a small way, then water would be a different sort of a substance. For example, we know that a water molecule is composed of two hydrogen atoms which are bonded to an oxygen atom with a shape that looks like a bent shape as given in the image. How would water be different if the shape of the water molecule was different? What if the hydrogen atoms bonded to an oxygen to form a linear molecule instead of a bent one? The answer to this question is not altogether simple. We don't know exactly how our hypothetical linear water would behave, but we do know it would be much different than ordinary water. For example, linear water would probably have a much smaller or a lower boiling point than ordinary water. In fact, it may be even a gas instead of a liquid at room temperature. Imagine what our world would be like if the water was a gas at room temperature. Then there would be no rivers, no lakes, no oceans, and probably no people. Since liquid water is such an important part of what composes us. As I have just mentioned, if these water molecules are bonded together in a linear shape, then nobody would exist. In addition, water remains liquid over a large temperature range, making it an ideal molecule to sustain life. So we just saw how chemists are interested in substances such as sand and water. But are these substances chemical? Yes. In fact, everything that we can hold or touch is made of chemicals. When most people think of chemicals, however, they may envision a can of paint thinner in their garage or recall a headline about a river polluted by industrial waste. But chemicals compose ordinary things too. Chemicals also compose the air we breathe and the water we drink. They compose toothpaste, Tylenol, and toilet paper. Chemicals make up virtually everything with which we come into contact. Chemistry also explains the properties and behavior of chemicals in a broader sense by helping us understand the molecules that compose them. As you experience the world around you, molecules are interacting to create your reality. Imagine watching a sunset. Molecules are involved in every step. Molecules in the air interact with light from the sun, scattering away the blue and green light and leaving the red and orange light to create the color you see. Molecules in your eyes also absorb that light and as a result are altered in a way that sends a signal to your brain. So molecules in your brain then interpret those signals to produce images and emotions. This whole process is mediated by molecules that creates that evocative experience of seeing a sunset. So let's move to our next topic, the scientific method, how chemists think. Chemists use the scientific method, a way of learning that emphasizes observation and experimentation to understand the world. The scientific method stands in contrast to ancient philosophies that emphasized reason as the way to understand the world. Although the scientific method is not a rigid procedure that automatically leads to a definitive answer, it does have key characteristics that distinguish it from other ways of acquiring knowledge. And these key characteristics include observation, the formulation of hypotheses, the testing of hypotheses by conducting experiments, and the formulation of laws and theories. The first step in acquiring the scientific knowledge is the observation. And the observation is the measurement of some aspects of nature. Some observations are simple, requiring nothing more than the naked eye. Other observations, they rely on the use of sensitive instrumentation, whereas the hypothesis is a tentative explanation of the observations we made, whereas scientific law summarizes the results of large number of observations and predicts the future ones. On the other hand, scientific theory is a model that gives us a deeper explanation for the underlying causes for observations and laws. As we discussed earlier, some observations can be made with the naked eye, others they rely on the use of sensitive instrumentations, while observations usually involves the measurement or the description of some aspects of the physical world. Observations also lead scientists to formulate a hypothesis. A good hypothesis is falsifiable, means that further testing has the potential to prove it wrong. Or hypotheses are also tested by experiments, highly controlled observations designed to validate or invalidate hypotheses. And the results of an experiment may confirm a hypothesis or show it to be mistaken in some way. Furthermore, these hypotheses may have to be modified or discarded or replaced by an alternative one. The new or revised hypothesis must be tested through further experimentation. Hypotheses, laws, and theories must be tested and validated by experiments in the scientific method. If hypotheses, laws, or theories are not confirmed through experimentation, they must be revised and tested through further investigation by applying the experimentative methodologies. So this is a general schematic of a scientific method, and we know that scientific method is a logical, organized approach that scientists use to investigate questions, test ideas, and build knowledge. It's a cycle of discovery and refinement, not just a set of steps, but a flexible process. Moreover, this diagram also emphasizes that science is iterative, not linear. Each conclusion can circle back, refining your ideas and methods until they withstand repeated testing. It's a powerful approach that you will use not only in labs but whenever solving real world problems. So, regardless of how these observations occur, they usually involve the measurement or description of some aspect of the physical world. For example, Antoine Lavoisier, a French chemist, made a series of controlled observations about the physical world. He measured the mass of different substances during the process of a combustion, which is the burning process. He observed that the mass of an object is a measure of the quantity of a matter within it. So Lavoisier, he burned substances in closed containers. He carefully measured the mass of each container and its content before and after burning the substance inside. So he noted that there was no change in the mass during the combustion. So Lavoisier made an observation about the physical world. So based on his observations of combustion, Lavoisier developed the law of conservation of mass, which states matter is neither created nor destroyed in a chemical reaction. The law not only synthesized his past observations but also predicted the future ones. So one or more well-established hypotheses may form the basis for a scientific theory. Theories provide a broader and deeper explanation for observations and laws. They are models of the way nature is, and they often predict behavior that extends well beyond the observations and laws on which they are founded. A good example of a theory is the atomic theory of John Dalton, where he explained the law of conservation of mass as well as other laws and observations by proposing that matter was composed of small, indestructible particles called atoms. And Dalton's theory was a model of the physical world. It went beyond the laws and observations of the time to explain these laws and observations. Theories are also tested and validated by conducting experiments. Note that the scientific method begins with observations and then hypotheses. Laws and theories are developed based on those observations. Experiments, which are carefully controlled observations, they determine the validity of the hypothesis, laws, or theories. If a law, hypothesis, or theory is inconsistent with the findings of an experiment, it must be revised, and new experiments must be conducted to test the revisions. Over time, scientists eliminate poor theories and good theories. Those consistent with experiments, they remain, while they also established theories with strong experimental support, which are the powerful pieces of scientific knowledge. People, they are mostly unfamiliar with science. Sometimes they say, oh, this is just a theory, as if their theories were more speculations. However, well-tested theories are so close to truth as we get into the science. For example, the idea that all matter is made of atoms is just a theory, but it is a theory with more than 200 years of experimental evidence to support it, including the recent images of the atoms themselves, which is shown in the image. These established theories should not be taken lightly. They are the pinnacle of scientific understanding. So the atomic theory has 200 years of experimental evidence to support it, including recent images such as this one of atoms themselves. This image shows 12 cobalt atoms which are arranged in a circle on a copper surface. So let's classify each statement as an observation, a law, or a theory. So the first statement, when a metal is burned in a closed container, the mass of the container and its contents does not change. It is an observation because this describes an event or a phenomena that has been observed. So the second statement, matter is made of atoms, it's a theory because the idea that matter is made of atoms is a conceptual explanation based on evidence and experiments explaining the behavior and structure of matter. The third statement, matter is conserved in chemical reactions. It is a scientific law as it consistently holds true based on empirical evidence and is fundamental principle in chemistry. And the last is when the wood is burned in a closed container, its mass does not change. It's also an observation. This statement notifying us that the mass of a wood in a closed container does not change when burned. So it is describing a specific event. So our next topic is analyzing and interpreting the data. Scientists, they take measurements as part of their observations, and such sets of the measurements are known as the scientific data. Suppose you are an early chemist trying to understand the composition of water. You know that water is composed of the elements of hydrogen and oxygen. You do several experiments in which you decompose different samples of water into hydrogen and oxygen, and you get the following results. The table below contains a set of measurements. Did you notice any patterns in the data? So the first and easiest pattern to see is that the sum of the masses of oxygen and hydrogen always sums to the mass of the water sample. For example, for the first water sample, 2 plus 2 grams of the hydrogen and 17.8 grams of oxygen, they sum up to 20 grams of the water. The same is true for the other samples as well. So recognizing relationships in the data is a skill that you will learn to develop throughout this course. So data is often visualized using graphs or images, and scientists must constantly analyze and interpret these graphs. For example, the graph shown in the figure, it tells us about the concentration of carbon dioxide in Earth's atmosphere as a function of time. Carbon dioxide is a greenhouse gas that has been rising as a result of the burning of fossil fuels such as gasoline and coal. When you look at a graph such as this one, you should first examine the x-axis and y-axis and make sure you understand what each axis represents. You should also examine the numerical range of these axes. For example, in this figure, the y-axis does not begin at 0 in order to better display the change that is occurring. How would this graph look like if the y-axis began at 0 instead of 290? Should also notice that in this graph, the increase in carbon dioxide has not been constant over time. The rate of increase is represented by the slope of the line, which has intensified since about 1960. So let's examine this graph. What was the concentration of carbon dioxide in 1970? So by intersecting and analyzing the graph, we found that it's 317 ppm. And what was the concentration of carbon dioxide in 2020? Which is 413 parts per million. And how much did the concentration increase between 1970 and 2020? So we will calculate by subtracting these two concentrations, which is the 93. Starting chemistry can feel overwhelming, but success comes down to mindset, habits, and effort, not just natural talent. So focus on conceptual understanding, practice regularly, use all the resources, learn from your mistakes, and manage your time wisely. So you don't need to be a genius to succeed in chemistry. You need to be curious, consistent, and open to learning. If you put in the work, ask questions, and stay engaged, you can do this. So chemistry also requires you to do calculations. You will be asked to calculate your answers and quantify information. So quantification involves measurement as part of the observation. It is one of the most important tools in science. For example, two samples of water may feel equally hot to your hand, but when you measure their temperatures, you may find that one is 40 degrees Celsius and the other one is 44 degrees Celsius. So it also requires you to do your work regularly and carefully. If you do, you will be succeeded. So by the end of this chapter, you learned how to recognize different chemicals which make up virtually everything we come into contact within our world. You also learn to identify and understand the key characteristics of the scientific methods, observation, the formulation of hypotheses, testing of hypotheses by conducting experiments, and the formulation of laws and theories. Finally, you also learn to identify different patterns in data and interpret these graphs. So if you have any questions or concerns, we will talk more in the incoming in-person class. Thank you.